Hello everyone and welcome to day 22 of the Jamb Physics in 40 Days series. To each and every one of you that has been following the series from day one, I would want to say a big thank you to you. Thank you for following the series, for dedicating your time and ensuring that you make it a date with us every day from day one up until day 22. You are the real MVPs. Thank you so much. And I also want to say thank you for sharing the videos with your friends and colleagues, everyone who also need this video. And if you have not done that, please, I want to implore you that you keep sharing the videos. Ensure you are subscribed to the channel as well. We want to ensure that we reach a wide range of audience that need this helpful content that we are making. So please subscribe to the channel, like the videos, and also share them. And if you are new to the channel, this is Jamb Physics in 40 Days series brought to you by Oya Learn, where we believe that when you dedicate within 30 to 45 minutes of your time daily, you'll be able to gather all the necessary tools that will help you ace Jamb Physics. So, peradventure, you are a student who is preparing for the Jamb exams, and one of the subjects you have chosen to write in that exam is physics. Then this video is made specifically for you. So trust me, you do not want to miss any of the videos in this series from day 1 to day 22 till the end of the series. Ensure that you follow each of the video because what we have done is that in each of those videos, we look at the individual topics in the Jamb Physics curriculum, and then we give you a crash course to it and also mention some things that are expected of you before the exams. And then we go on to solve past questions in those topics while giving you tips that helps you solve those questions with accuracy at all times. So please ensure you follow the series and don't forget to subscribe to the channel. Please hit the subscribe button and the notification bell icon so that you get alerted every time we put out a new content. And also ensure that you share the videos amongst your friends who are also preparing for the exams so that we can help them to also ace Jamb Physics. And also to infuse a bit of fun into your learning time, you can download the Exam Fun app. The link to that is in the description box of this video. The app is created in such a way that it makes your learning experience a fun one. It's different from the regular apps that you have that just solve questions alone. In this one, it is like in a game-like setting where you solve questions at different levels whilst earning points and also earning money at the same time. So you can earn while you learn, and it's all a fun activity. So trust me, you don't want to miss that app. Ensure that you click the link and download the app today. And if you have any question at all that you'd like to share with us, please put it in the comment section. We will definitely attend to every one of your comments. So thank you for doing this. Now to get to the business of day 22, what we'll be looking at in this video is the characteristics of sound wave. And we've been following waves for a while now from day 20 where we started waves in total. But here now we're just focusing on the characteristics of sound wave. And what Jamb expects of every candidate concerning this topic is that you should be able to differentiate clearly between noise and musical notes. Now, beyond the fact that musical notes sound palatable to the hearing, one thing that actually differentiates them is the pattern of the pitch. For musical notes, we have a regular pattern of vibrations, but for noise, it is an irregular pattern of vibrations that constitute what we know as noise. So both of them are sound waves, but when one has regular vibration, the other has irregular vibrations. So, and of course, the irregular vibrations will not sound nice to the hearing. So that is why it is called noise. While the regular vibration sounds palatable to the hearing, so they are called musical notes. Now, beyond this, you should also be able to tell us some characteristics of sound waves, such as the quality of a sound wave, the pitch of a sound wave, the intensity and the loudness of sound wave. And you should also relate this with the applications in musical instruments. Now, of course, you know, when we talk musical instruments, we are looking at things like brass instruments, woodwind instruments, percussion instruments, and the likes. You should be able to list those types of instruments. And then thirdly, they expect that you should be able to describe the overtones produced by vibrating strings and their columns. Now, there's a general equation in this case where we have F naught equals 1 over 2L to the square root of T over U. And each of these have their definition, so you should be able to work with this particular equation. And beyond this, there are other equations that we have for the different harmonics as well. So please get yourself abreast with those equations, because there are questions that you will likely face on vibrating strings as they were. Now, another thing that they expect of every candidate is that you should be able to tell about acoustics and their examples of the acoustic examples of resonance. That is, define what resonance is and give examples of resonance. Now, when we talk resonance, it's when a vibrating object sets another object in vibration at its own natural frequency. And I'm sure that you would have heard of cases where opera singers, for example, are able to shatter glass with their voice. That's an example of acoustic resonance. And it goes beyond this, and there are quite a lot of applications to this. So please ensure that you go through the resonance and examples of resonance. And then finally, they expect that you should be able to solve cases of frequencies of notes emitted by air columns for closed pipe and open pipe, relating this with the length of the pipe. Like, for example, when we're talking about open pipes, let me do closed pipe and open pipe like this. Closed pipe and then open pipe. Now we have what we call the harmonics. Now we have the first harmonic, second harmonic, third harmonic, fourth harmonic, and so on. Now the fundamental frequency, which is the first harmonic for a closed pipe, is given as, now we call that F naught, and this equals fundamental frequency for closed pipe, that is V over 4L. Whereas in open pipe, the F naught here is V over 2L. Now, as you go on, when we get to second harmonic, it changes what we have here. So that is what you're going to have here, which is F1 now, which is the second harmonic or first overtone. Now, this means first overtone but second harmonic. Now, this would be given as 3 F naught. That is 3 multiplied by V over 4L. But in this case, F1 is 2 F naught for the case of open pipe. And then it continues like that, where this one would then be 5. And then this one would be 7. So we use odd numbers when we are working with closed pipe. So basically I can say Fn equals N into V over 4L when we are talking about odd numbers. For odd numbers in this case. For odd numbers for closed pipe, but when it comes to open pipe, your Fn is going to be NF naught. So that is what we're going to be having here is F2. That is what we have here is 3 F naught. And then F3 here will be 4 F naught. Now take note, these are overtones. Okay? First overtone, second overtone, third overtone. Now the first overtone is known as the second harmonic. The second overtone is known as the third harmonic, and it continues like that. So it's important that you are able to relate this equation whenever you are solving problems on closed pipes and open pipes. Now this is what is expected of you. However, for a deeper understanding on this topic, you can check out our video where we explain the characteristics of sound waves in greater detail. Now that video is not in preparation for Jamb, or for you to understand the entire concept of sound waves as it were. So we touch every detail and ensure that we explain with enough examples. So please check out the video to get a fuller understanding on this topic. But for the purpose of Jamb preparation, we believe that you should have gone through all of that. So now we'll be looking at past questions on these topics, and then we'll be giving you tips that will help you solve with great accuracy every time you find a question on characteristics of sound waves. So if you're ready, get your materials and let's solve some past questions. This question says, musical instruments playing the same note can be distinguished from one another owing to the difference in their... Now, these are some of the characteristics of sound waves. Right? Now, when you play two musical instruments playing the same notes, like for example, if you are playing a particular song that has its own tonic sulfur on a piano, and another person is playing the same thing on a violin, it is possible that they will have the same loudness, so you will not be able to distinguish it by loudness, because loudness is only looking at the amplitude of the sound wave that you are creating. And when it comes to intensity, that's looking at the power of the wave, and both of them can give you the same power of wave, so you still can distinguish based on intensity. And the same thing applies to pitch, because pitch is only looking at how high or how low the note is. So if both of them are playing on high notes, they could sound alike. If they're playing on low notes, they could sound alike. So you can't distinguish by pitch as well. But when you look at quality, now another name for quality is timbre, right? This is what we use to actually distinguish between the sounds from pianos, from violins and the likes, because this is looking at the note itself in itself and telling us the quality of this sound from the other. So if you want to distinguish between sounds from two instruments, we look at the quality. It's just the same way when a person is trying to mimic the voice of another person, right? The way you would know that this is not the actual person is by the quality of the notes, the sound that the person produces from their mouth, right? So in this case, the answer is quality, so we go with option A. In this question, we are asked that the pitch of an acoustic device can be increased by... Now, pitch is looking at how high or how low a note sound, and that is a function of the frequency of the sound wave's source. So when the frequency is very high, the pitch is also going to be very high. And then when the frequency is low, you're going to produce low note sounds. So like when you're singing in baritone, you're producing low notes, so the pitch is low. But when you're singing in soprano, for example, that is a very high note, so the frequency ought to be high. So that is, pitch relates with frequency. So to increase pitch, what you have to do is increase the frequency. So the answer is option C. If a sonometer has the fundamental frequency of 450 Hz, what is the frequency of the fifth overtone? Now, I did mention at the beginning of the video that when it comes to strings, you have to understand how to find the individual, whether from fundamental frequency to the first overtone, second overtone, third overtone, and so on. There is an equation for each of these. Okay, now the equation works well when we work with harmonics. So in case of harmonic, the first harmonic, which is the fundamental frequency F0, is given as V over 2L. And then as you go down, when we get to F1, which is the first, this will be the first overtone. First overtone become 2F0 and so on. So second overtone, 3F0. Third overtone, 4F0. Fourth overtone is 5F0. And then the fifth overtone would be 6F0. So that's the relationship between the overtones and fundamental frequency. So since we want to find the fifth overtone, that is in our solution, our fifth overtone equals 6 multiplied by the fundamental frequency, which is 450. Now, what does this give us? 6 times 0, that's 0. 6 times 5, that's 30, so 0 carry the 3. 6 times 4 is 24. Now 24 plus 3 will give you 27. So 2700 hertz. So the answer is option A. In this question, we see that the lowest note emitted by a stretched string has a frequency of 40 hertz. So, and then we are asked how many overtones are there between 40 hertz and 180 hertz. So let's solve. The first overtone is going to be twice of 40, 2 times 40 hertz, and that will give us 80 hertz. That's the first overtone. Now the second overtone will be 3 times 40 hertz, and that will give us 120 hertz. Now by the time we get to the third overtone, that will be 4 times 40 hertz, and that would give us 160 hertz. Then the fourth overtone will be 5 times 40 hertz, which will give us 200 hertz. Now the question says between 40 to 180. So that is, we are not supposed to get to 200 hertz. So that tells us that this lies at the third overtone. So our answer will be third overtone, which is option B. If the distance from a point source of sound is doubled, by what factor does the intensity decrease? Now this already lets us know that the relationship is an inverse proportionality. So that is, we can say the intensity is inversely proportional to 1 over distance. But the actual distance is squared of the distance, right? So if you double this, that is, what would then happen to distance when you double intensity? That would be 1 over 2 in bracket squared. So that will give us 1 over 4, right? So this would be the increase that should happen. So when you are checking the decrease, you have to do the reciprocal of this, so that it will decrease by 4 factors. So our answer in this case is option A. In this question, we are told that the turning fork of frequency 340 Hz is vibrated just above a cylindrical tube of height 1.2 meters. So if water is slowly poured into the tube, at what maximum height will resonance occur? Now, you could be asked to also find the minimum height, but in this case, we are asked to find the maximum height. So I'm going to show you how to do both of them, just in case you find a question like that. So let's solve. So first, we know that frequency is 340 Hertz. V is also 340 Hertz. So what we are looking for is L. Now, the fundamental frequency is supposed to be V over 4L, right? Now, what this implies is that the first length we're going to have, let's call that L1. That would be V over 4F, right? And this would give us what? So L1 here will be 340 divided by 4 times 340. Now, if you break this, what we have is 1 over 4, which is 0.25. That's the first case now. Now, to find L2, what we're going to be doing is L2 equals, remember we use odd numbers because it is closed at one end. So that will be odd number, so 3F0. And what we have as this case now, what we have here, that will be 3 multiplied by, now we have V, which still remains 340, all divided by 4 times the frequency is still 340, right? So if this cancels out, we have 3 over 4, that will give us 0.75. Now we can continue to get the next one, say L3, where we'll be using 5 now. So that will be 5 multiplied by V, which is 340, all over 4 times F, which is also 340. So this cancels out, and we see that the length here in this case is 5 divided by 4, and that will give us 1.25. Now, if you observe, you see that in the question we are told that the length, that is the height of the cylindrical tube, is 1.2. So it means this will not be effective for us. So this one is cancelled out in the case. So we are asked to now find the maximum length for resonance, where resonance will occur. So to find the length where resonance will occur, for the first one that we did here now, which will be the maximum length. So max length of resonance would then be the length of the tube itself, which is 1.20, minus the length at fundamental frequency, which is 0.25. Now this will give us 0.95 as our answer, right, in meters. So that is, for this question, the answer is option A. However, if they're asking you for the minimum length for resonance to occur, since L3 cannot work because this is more than the length of the cylindrical tube itself, then I'll be using L2. So the minimum would then be 1.20 minus 0.75, and that will give us 0.45 meters. So you see that even this, the answer is amongst the options that we have here. This is just to show you that the question can be twisted in any form, right? But the question is maximum height, and this is the maximum height that we have, which is option A. A note is called an octave of another note when, now if you're yet to be subscribed to the channel, I'd like to implore you at this point to please hit the subscribe button. It's only going to take a second of your time, so please click the subscribe button and also hit the notification bell icon so that you get alerted every time we put out a brand new content. And if you have any question at all on what we are doing so far, or perhaps during your study time you come across a question that you need help solving, please put those questions in the comment section and we'll definitely attend to every one of your questions. So now in this question, we're supposed to identify how you can tell that a note is an octave of the other, that is an octave higher than the other. But I'll be killing at least 2 or 3 birds with one stone in this question by describing what each of these options says. So firstly, the question is asking that the note is an octave higher. So when a note is an octave higher, like for example, if the frequency of the first note is say 440 hertz, and then you play an octave higher, what will happen is that an octave higher is going to be twice of the frequency of the first note. So that would be, if it's 440, it becomes 880 hertz. So twice of the frequency. So in this question, the answer is option A, that is, its frequency is twice that of the first one. However, if they were saying an octave lower, of course, that would mean that it is half of the original frequency, which should have been option B. So please keep your eyes open for such kind of question. What matters is the way the question is set. This one we are saying an octave of another, that is, it is higher. So if they say it is half, as in an octave below, then that will be half the first frequency. The question could also be twisted and said that maybe a first note is 440 and then another note that is 220 would be said to be what? In that case, that will be an octave lower. But if they double it, that will be an octave higher. I hope you understand what I'm saying in this case. And then when you look at what we have in option C, saying the notes have the same fundamental frequency, this is one of the ways you can tell 2 sounds apart. Like if you are playing the same sound on a piano and then the same sound on a violin, for example, even though they have the same fundamental frequency, the only way you can tell them apart is by the quality of those notes. It's just like one of the questions we have answered in this series when we're talking about qualities of a sound note. And then when you look at option D, it says its periodic time is twice that of the first note. Now you know that period is 1 over f, right? So if you are saying twice of period will be 1 over what? Right? That is, you multiply this by 2. That will be 2 over f, right? So by the time you're trying to find the frequency, you see that you're actually reducing the frequency by 2. So that is dividing the frequency by 2. This option D is similar to what we have in option B. That is, these two tell us the same thing. But in this question, the answer is A. That is, you double the frequency. When the bottom tip of a vibrating tuning fork is held in contact with a wooden box, a louder sound is heard. Now, this phenomenon is known as, now in this case, what you see happening is that when you take the vibrating tuning fork and place the bottom tip to that wooden box, it will cause the wooden box to begin to vibrate at the natural frequency of the vibrating tuning fork. Now, since both of them are at the same frequency now, they would interfere with each other, causing the amplitude to increase, which is why you see that the sound becomes louder. Now, that phenomenon is actually what is called resonance. That is when a vibrating object forces another object into vibration at its natural frequency. However, in the case of beat, the frequency has to be different for when interference is occurring for you to have what we call a beat. So it's going to be rhythmic pulse to make a beat because the frequency is different. Now, in the case of echo, that's a reflection of sound wave. That is when you hear a sound wave after some time that it has been produced. That would be echoing. And then for reverberation is when there's continuous reflection such that it then produces what you know as prolonged sound. That is, the sound starts and ends, but it sounds as if you are still hearing more and more of it, as is a prolonged note, because you have multiple reflections occurring. That would be for reverberation. But in this question, the answer is resonance, which is option C. Two tuning forks of frequencies 256 Hz and 260 Hz are sounded close to each other. What is the frequency of the beat produced? Now you see that the frequencies are different, so when they interfere, it produces a beat. And to find the frequency of the beat, this is what we do. The frequency of the beat becomes F2 minus F1. That would be 260 Hz minus 256 Hz. That means the frequency of the beat is 4 Hz, which is what we have in option B. Please, if you're here to be subscribed to the channel, I'd like to implore you that you take a moment to click the subscribe button and the notification bell icon so that you get subscribed to the channel and also get notified every time we put out a new content. And also do not forget to check out the link in the description box to help you download the Exam Fun app, which is an app that makes your learning experience fun and worthwhile. Because not only do you get to enjoy while you solve questions, you also earn as you learn. So please click the link, download the app, and if you have any question at all, please put it in the comment section. We will definitely attend to all of your questions. Now, to answer this question, we are told that a slight loading of a tuning fork has the effect of, that is, when you add mass to a tuning fork, either by sticking plasticine to it or other materials like that, what will happen to the sounds produced by that tuning fork? Now, there's a relationship between mass and frequency, and it is given as frequency is proportional to 1 over the square root of mass. This is the relationship between mass and frequency. So when you add load to a tuning fork, it means that you are increasing the mass, right? And when you increase the value of this mass, what will happen to frequency? Since it is inverse proportionality, there should be a decrease in the frequency as you increase the mass. So the answer here is option C, which says decreasing its frequency. In this question, we have that a piano wire 0.5 meters long has a total mass of 0.01 kilogram. And then it is stretched with a tension of 800 newtons. And we are asked to calculate the frequency of the wire when it sounds its fundamental note. Now, in this case, we are focusing on the fundamental frequency. But the same question can be spun around where you are then asked to find the frequency of the first overtone, second overtone, third overtone, and so on. Now, we have already shown you the relationship between fundamental frequency and the different overtones that we have. So that means if you can get the fundamental frequency, you should be able to find any overtone you're asked to find, whether it's the first, second, third, fourth, or no matter the number of overtones you are asked to find. But bear in mind, you are working with a string here, not a pipe. So what do we do to find the fundamental frequency? At the beginning of the video, I did give us an equation for questions like this, where we have that the frequency is given as 1 over 2L square root of T over. Now this symbol is mass per length, okay? And mass per length is given as M over L. So let's find the mass per length for this piano wire. So this would be, the mass is 0.01 kilogram divided by the length, which is 0.05, and this would give you 0.02 kilogram per meter, right? So now that we have our mass per length, let's now find the fundamental frequency. So for the fundamental frequency F, that would then be 1 over, remember fundamental frequency, so let's call it F naught. So 1 over 2 times L, which is 0.5. Now multiply that by the square root of tension, 800 newtons, all divided by the mass per length, which is 0.02. Now if you compute this, this would give us 1 multiplied by, this one is square root of 40,000. And the square root of 40,000 is 200. 200 times 1 still gives us 200. Frequency is measured in hertz. So in this question, our answer is option A. However, if you're asked to find the first overtone, for example, remember that the first overtone of a string is given as twice the fundamental frequency. So you just multiply this by 2 and then that will give you 400 hertz. So if you are asked to find the second overtone, that will be 3F naught. And then if you are continuing like that, F3 would be what? 4F naught, and so on. So depending on what the question requires of you. But in this case, since it's just fundamental notes that it sounds, F naught will be 200 at option A. Which of the following instruments has a pure tone? Now, when you hear the word pure tone, it refers to the fact that the instrument produces a tone that has only one frequency. It is not accompanied by any overtone whatsoever, just a single frequency. Now, most of the musical instruments we have produce complex tones because they give you a frequency and accompanied by their overtones, right? But if you want a pure note, that is a note that just has a single frequency, the instrument you use to produce that is a tuning fork. So the answer here is option C. A wave of frequency 10 Hz forms a stationary wave pattern in a medium where the velocity is 20 centimeters per second. Now we're asked to find the distance between adjacent nodes. So let's visualize what a stationary wave looks like. So it goes along this path. Now, this is a stationary wave, okay? And the distance here is for a complete circle, which is known as wavelength lambda. But this will be a node, which makes this antinode and this antinode. So you see that the distance between adjacent nodes is only half of the wavelength. So what we have to do is to first find the wavelength, then find the half of that wavelength to get the distance between adjacent nodes. So first, let's find the wavelength. So wavelength lambda would then be velocity over frequency. And the velocity is 20 centimeters per second over frequency, which is 10 Hz, the same thing as 10 per second. So that cancels out, leaving the wavelength as 2 centimeters. Now, distance between adjacent nodes would be lambda over 2. So that's 2 centimeters divided by 2, and that will give us 1 centimeter. So the answer here is option A. This question is a reverse case scenario of one of the questions we have solved in this video. And this one says of two identical tuning forks with natural frequency 256 Hz. One is loaded so that 4 beats per second are heard, when they are sounded together. Now, what is the frequency of the loaded tuning fork? Now, when we're working with beats, we know that the frequency of a beat equals the difference in the frequencies of the individual tuning fork in this case. So since the frequency of the beat is 4, so 4 equals F2 minus F1, which is 256 hertz. So F2 therefore becomes 4 hertz plus 256 hertz, and this will give us 260 hertz. So the answer is option A. All of the following frequencies are overtones of 320 hertz except, so you know, to get overtones you have to multiply these by 2, 3, 4, 5 and so on like that. So basically, to get the ones that are overtone, let's just divide by 320, and then if we get a whole number as our answer, then it is an overtone of that. Like in the first case here, we have 960 hertz. So 960 hertz divided by 320, that's going to give you 3. So that means that 3 multiplied by this gives you 960. That will be the second overtone for 320 hertz. Now 640 divided by 320 will give you 2. That means this is the first overtone if this is a fundamental frequency. So it's an overtone of this as well. And then when we apply it with the others, you will find that this would give you 4, while this would give you 5. That is, this would be the third overtone, and then this would be the fourth overtone. But this does not divide to give you a whole number, because it will give you 1.6 something thereabout. So that tells you it's not an overtone of 320 hertz. So, and the question says all the frequencies are overtones except, so this is the only one that is not an overtone, so we go with option C. Now, if you want to practice and get better, one sure way to do that is to solve many questions. So you can download the Exam Fund app, which has a lot of questions in all subjects of your choice, and then you can get to practice. And the beautiful thing about that app is that it is created in such a way that it infuses a lot of fun into your learning time. So you get to solve questions in a fun environment and also earn while you learn. So download the app today by clicking the link in the description box of this video. And also do not forget to subscribe to the channel. Please, we need you all to subscribe so that we can keep making more helpful content like this. So please click the subscribe button and also the notification bell, the bell icon there, so that you get notified every time we put out a brand new video for you. And if you have any question at all, please put it in the comment section. No matter what the question is, it's about what we are doing presently, or if there's any subject, any topic you are working with and you're finding problems with it, please drop questions on it in the comment section, and we'll definitely attend to all of your questions. So please keep following the series. It still continues. We'll continue in day 23. Thank you so much for your love and support. I'll see you in the next video.